So I told you I was going to post all the material from test 3 this morning, but I kind of got busy this morning, so I didn't get around to it. But after class today, I will post all the stuff from test 3 so you can start studying.
Also, do you read your messages in Canvas, or should we email you directly to your email?
Directly is better because they don't show up sometimes in Canvas.
Right.
I mean, they do, but they're not. It's not obvious where they show up. I have to like click and go through them. So what was I going to say? Yeah. So the other thing is, remember the test is going to be Tuesday. I'll send an announcement out just to make sure everyone's on the same page. And I'm moving the quiz schedule up by 1 day. So instead of being assigned on Saturday, due Tuesday. It'll be assigned on Friday, due Monday.
This Friday.
Yeah, what we did since test 2, there'll be a quiz on it on Friday, due on Monday. Right? Then we have a review session on Monday. It was weird yesterday because of Memorial Day, but otherwise it's on Monday. So that's the day before the test, and we'll review on Tuesday a little bit, right? During the class, just like we've been doing, right? So is everyone clear the shift? Okay, so I just wanted to do one quick example or part of an example, depends how far we get, on centripetal force, right? So this is what the new thing that we started on yesterday. And we just started. We just did one example, and we're going to do a few more examples, but we'll do the rest of them tomorrow. So this is like the second example after the one we did yesterday, which is the yo-yo one. So here's another one. So a car is traveling over a semi-circular hill. So hills are not circular, but you can sort of model them as being circular. You can approximate them as being circular, is what I'm trying to say, with a radius of 5 meters. So the question is, what is the maximum speed the car can be moving at the top of the hill before it leaves the surface of the road or hill, whatever it is you're talking about. Okay, so the sketch looks like this. I did the sketch ahead of time for once. I should always sort of do these things. All right, so you have this car, which is that box at the top, and this is a hill. So obviously hills aren't circles, right? But they look sort of like circles in some sense. So the car's here, and it's moving at some speed at the top, right? You're going over the top of the hill. So that means your velocity is like this, the car's velocity. Oops, sorry. And so the question is, how fast can you go at the top before you leave the hill, just in terms of the radius maybe, or in V, how fast you're going. So that's the sketch, right? And this is, a typical coordinate system. So, unless you're talking about an incline, it's just, the typical way you draw a coordinate system.
Are we talking about like driving off the hill?
You'll see what
you catch air?
Right. Okay, so this is a centripetal force problem. The reason why it's a centripetal force problem is because whenever you're going around a circle, even part of a circle, in this case it's not an entire circle, it's half a circle, but whenever you're going in a circular path, no matter what's going on, you always have to look at centripetal force to analyze this thing. So what we're going to do is do the same thing we did yesterday. So what we're going to do is sketch the typical forces acting on the car. In other words, not everything but the centripetal force. So, we're going to look at the centripetal force eventually, but let's just draw the forces that we're used to drawing up until this point, right? That aren't the centripetal force. So just think of the car. So let me get rid of this V. The velocity, the car is moving, but we're talking about forces here, not velocity. So to make it less confusing, I'm getting rid of the V. Okay, so if you just have a object on the surface, like on the sill. Right, yeah, the weight force, which goes down, like that. And which way do you think the normal force? So this is, a circle. So it's not level, but you're at the very top of the circle. Which way do you think the normal force would be going? Yeah, it's just going straight up because that's, where it makes contact with the circle is at the top. So it goes straight away from the circle, right? So it's just straight up. Oops. I don't know what's going on today. But the next question is, are these radial forces, right? That's the new thing that we're talking about. These new types of forces called radial. So radial means, are they going toward the center of the circle or away from the center of the circle?
Well, weight is going
towards the center.
yes.
Fn is going away from the center. So these are two radial forces. So basically the radial direction is the y direction for this case. There's more technical ways of doing this, but when you first start, this is the best way to do it, right? So we can say the radial direction is the y direction. So what we need to do is sum, the radial forces, that's rad, I put RDD for some reason. So in other words, it's the summing the forces in the y direction. So what do you get when you sum these two forces, which are completely in the positive negative y direction?
Fn minus W.
Yep. So that's the first step, is to sketch the forces that aren't the centripetal force, figure out what direction's the radial direction, and then sum those radial forces, just like we just did. Now, let's sketch the centripetal force, right? So you always have to do this if something's going in a circle, right? This procedure. It gets easier to do when you see it a few times. It's actually not too bad.
Is there a C in the word centripetal?
What was that?
Is it centripetal?
So, I mean, depends how you want to say it, but I usually say it's a triple.
Okay. So there's no second C?
No. No.
Oh, I've been pronouncing it wrong apparently.
It's fine. It's not a big deal as long as you know what we're talking about, right? Okay, so which way does this triple force go? Towards the center. So here, if you're at the top of the circle, which way is towards the center? Down, right? Right, this triple force always goes towards the center. In this case, negative y. So then, I'm just typing it out in detail here. You don't really have to type all this, but some of the radial forces is equal to the centripetal force with its proper sign. So you got to get the signs right. So which way is the centripetal force going? Negative y or positive y?
Negative.
Negative. So what you do is you sum these, right? That's what you do first. And you set that equals centripetal force with its proper sign. Since it's in the negative y direction, you write minus FC because it's in the negative y direction, right? Same direction as W, they're the same sign. So that's it. That's how you write the equation down, which gives you how to, which lets you figure out how to analyze this thing. So let's do one more step and write down the weight. So the weight is mg. We know that. Centripetal force is something new, but it's m v squared over r, and that's the v that we're trying to find. Okay, so let's do something, and before we answer this question, let's figure out something first. Let's solve for Fn, which is the normal force acting on the car at the top. So you just add mg to both sides, right? And you can simplify it a little bit because there's an m on both sides. So you get, g minus v squared over r, right? Because when you do the math, it's mg minus mv squared over r, and then you pull out the m, and you get g minus v squared over r. All right, so let's look at this quickly. And there's one more step we need to do, and then we can go. But let's just analyze this. So what happens to Fn if v is 0? Let's say you're stopped on the top of the incline, right? You're not moving. what is the normal force? It's equal to the weight, right? So what happens if you go faster from 0? You go from 0 to some other speed bigger than 0. What happens to the normal force? No, you're subtracting. It gets smaller, right? So the normal force gets smaller as v gets bigger. Eventually, what do you think happens if you're going fast enough?
You overcome this problem.
What's the smallest Fn can be? 0. What does it mean if the normal force is 0? It leaves the surface, right? So when the normal force becomes 0, when you're going fast enough, then Fn becomes 0, right? So when the normal force becomes 0, the car leaves the surface. That's why you fly off the surface, right? You're going over a hill because you're going to... no, this is like, here, I'll show you some, when we finish this, I can show you something quick.
It's
So-
kind of like parasailing.
I guess. I need to think about that more. So if the mass isn't 0, you can divide out the mass, right? Because you divide by mass. You divide mass out, right? And then you get the parentheses has to be equal to 0. So you get something pretty simple. You get G is equal to B squared over R. So then if you solve for V, what do you get? You multiply by G to get, you multiply by R, sorry, to get rid of the R, and then you take the square root. And this is just how fast you're going. It's the magnitude of the velocity. It's not, it doesn't, I'm not talking about the direction, just how fast you're going. So it's just plus the square root of RG. So that's it. That's the answer, right? So it only depends on the radius of the hill. So there's one more thing we can ask here, and then you can go. Suppose R is different, right? Suppose you're on different hills, right? And you're trying to figure out how fast you can go before you leave the surface. If R becomes smaller, what happens to V? In other words, if you go over a smaller radius hill, what happens to V? It gets smaller, right? So if you look at a speed bump, what is it? It's a little tiny hill, right? With the radius of, I don't know what it is, but it's not that big, right? It's like a quarter of a meter or something like that. So if you put in R as a quarter of a meter, that's how fast you can go over a speed bump before your, tire bumps off a speed bump, right? That's how speed bumps work, or how going over. All right, the smaller they are, the slower you need to go so that your car doesn't jolt off the speed bump, right?
Yeah.
That's it, right? So, I mean, you can make up a value for R, say it's 10 meters, right? You just plug it in, 10 meters times 9.81 times this, take the square root, that's how fast you need to go, right? All right, so does that make sense? Okay, so we'll do a couple more centripetal force problems tomorrow, and we'll finish that up with centripetal force.